Welcome back. In the last session, we were solving problem number 4, classroom workbook problems, and we were in between, and I explained like case 1, when Vi is minus 1 volt, when Vi is less than minus 1 volt, your diode D1 will be on and D2 will be off, because D2 will be on only when Vi is greater than 2. That is what we had seen in case 3. Then D1 is on. When D1 is on, then your V0 will be minus 1, but in between minus 1 to 2, because only when Vi is greater than 2, then only your D2 will be on, but in between minus 1 to 2, both will be off. When both are off, right, when both are off, simply your V0 is tracking your Vi. Therefore, no D1, no D2 means then no control, then simply your V0 will be controlled by Vi. Okay, now this is what it is. Once you know, then what is your transfer curve? Okay, but one thing, this is fine. Therefore now, but actually if you see the problem, we assumed that when diode D1 is on, I told it is short circuit, right? That is what it is, short circuit. And similarly when D2 is on, I took short circuit. But strictly speaking, he is saying that what is the problem statement? 2 silicon diodes with a forward voltage drop of 0.7. Therefore, but what we took ideal model. If you take ideal model, this is what we are getting. But if you consider practical model, then this is not short circuit. We have to put 0.7 volt battery with respect to the power bias voltage. Then only you will get it. Okay. Can I do some correction? But you can continue. Whatever you got, that is fine. Okay. Therefore, if you ask me the ideal model, therefore, if you ask me your ideal model, if you take ideal diodes, then what is your transfer curve? Your transfer curve is nothing but what? This is what your Vi and this is what your V0. Tell me what are the breakpoints? Minus 1 to 2, right? This is what is minus 1 and this is what is 2. Therefore, minus 1 volt to 2 volt. Then if it is Vi less than minus 1, your output is minus 1. It is exactly minus 1. When input is greater than 2, your output is 2. Your output is 2. But in between, it is tracking your, therefore this is what? Your V0 is equal to Vi. This is what it is, right? Therefore, if you consider ideal diodes, for what input range, your output is equal to input, that is nothing but minus 1 to 2. But if you consider practical diodes, that is what is the problem statement. If you consider practical diodes, this is what your Vi, this is what your V0. Now let me correct something. Therefore tell me this is what is true, but now I told that when this is minus 1, at least we need 0.7 voltage drop. Therefore it should be what? When I say this is minus 1 and this should be minus 1.7. Only when it is minus 1.7, minus 1, minus of minus 1.7, then 0.7. Therefore, instead of saying for minus 1 for ideal diode, now we have to say minus 1.7. Therefore, now the correction is, it's not 1, it is minus 1.7. If it is minus 1.7, then tell me what is this? This is already the battery, but now the diode what you have, it will have, I told, right, this is related to second approximation, where we are considering the cut-in voltage. Then we need to replace your diode with a battery. Which battery? This is what is the battery. This is what is your 0.7. Then it is nothing but what? Minus plus, it will be minus 1.7. Minus 1.7. That is what your output voltage. Similarly, therefore now, this is what is your minus 1.7. Now, similarly, if you see here, when I say this is what is 2, at least we need to have 0.7 voltage drop. Therefore, this voltage should be greater than 2.7. Then only this will be on. When it is 2.7 and this is 2, 2.7 minus 2.7. Therefore, it should be more than 2.7. But if it is less than 2.7, your diode D2 is also off. Then it is V0 is equal to Vi. Now it is when it is more than 2.7, then only, then it is nothing but your forward bias diode. Therefore, it is like this. The diode is represented with a battery, second approximation, which I already explained before. And this is what your 0.7. Therefore now what is this? What is your V0? Your V0 is 2.7. This is what is using second approximation. Okay. Now what are the breakpoints? Breakpoints are minus 1.7, 2.7. Therefore minus 1.7 and 2.7. Therefore this is what is our 2.7 volt and this is what is our minus 1.7 volt. Then tell me when it is greater than 2.7 volt, sorry, when it is less than minus 1.7, it is minus 1.7, it is minus 1.7, greater than 2.7, this is also 2.7, in between it is tracking your input. Therefore this is 2.7 and this is minus 1.7. In between your V0 is equal to Vi. Therefore what is the answer? It should be having in between minus 1.7 to 2.7, your output is tracking to your input. Therefore what is the answer for the problem number 4? Answer is D. Answer is D. If you consider practical diodes, if you take ideal diodes, minus 1 to minus 2, simply 0.7 won't be there. But he's saying specifically that you have to use a forward voltage drop of 0.7. Okay, take it. You try to again, if you write again and again, you will remember. Okay. Therefore, case 1 is ideal diode, case 2 practical diode. Therefore, you will understand. With this problem is over, you could find for what input voltage range your V0 is equal to Vi. That we got within minus 1.7 to 2.7, your V0 is equal to Vi. But now if this is what is the transfer curve, right? If I give a sine wave, instead of giving some Vi, if I give a sine wave, what is your output? That also we can find. Okay. I'll give you 1 more minute, you complete, then we'll see if I give a sine wave there, problem is over, but I'm just asking you, if Vi is sine wave, what is your V0? It is also a clipper. Using the transfer curve. Now the transfer curve is describing your circuit for any value of Vi from minus infinity to plus infinity. Okay. Because we already have the curve. Therefore now tell me, if I say this is what is my input, this is what is our sine wave, let us say this is sine wave is given at the input. Okay. Now we need to find output. Let us say the peak value, this is 5 volt and minus 5 volt. 10 volt peak to peak sine wave is given. Okay. Now for this, what is your output? First of all, you need to get breakpoints. Breakpoints are minus 1.7 and 2.7. Minus 1.7, I can say this is minus 1.7 and 2.7, you can say this is what is our 2.7. Therefore now tell me, Above 2.7, your output is 2.7. Okay, your output is 2.7. Below minus 1.7, your output is 1.7, minus 1.7. In between whatever you have, that is simply tracking. Whatever input you have, it will track. Therefore, in between 2.7 to minus 1.7, this is what is tracking. Therefore, can I say this is also clipper, but positive as well as negative clipper. If your input is more than 2.7, it is clipping, and when input is less than minus 1.7, it is clipping. Only if input is having in between minus 1.7 to 2.7, it is tracking. Your output is tracking to your input. All other signals are clipped. Okay, therefore it is a clipper. Take it. Then we'll solve problem number 5. Done? Okay. Now problem number 5. In the following, okay, a voltage 1000 sin omega t is applied across YZ, assuming ideal diodes. The voltage measured across WX is, okay, circuit is, this is the circuit, and this is what is Y, and this is Z. Now this is what is W, and this is what is X. Okay, this is what is 1 kilo ohm, and this is also 1 kilo ohm. Fine. If this is the case, what is he saying? YZ. Across YZ, voltage across YZ is equal to 1000 sin omega t. This is what is applied, and diodes are ideal. Then what is asking is voltage across WX. Okay, there are all 4 options. Okay, let's see. The problem is with you. Now, let me call this as diode D1, D2. It's not given in the problem, but I'm just taking D3, D4. Okay, where your input? Your input is at YZ. Now, just to make it simple, just for your understanding purpose, can I draw the circuit in a different way? Actually, redrawing. What I do, this is what your YZ, because I'm applying between Y and Z, Y I'm taking as this. Therefore, if I just convert into, this is what is your 1 kilo ohm resistor, but this is what is my Y. Okay, and this is what is my Z. Okay, for Y, What is your diode D1? Your diode D1, okay, this is what is connected to like this. This is what is your diode D1. Diode D1, N is connected, okay. Similarly, diode D2 also N is connected. Diode D2 also N is connected. This is what is the diode D2. Then other terminal, for D1 other terminal is nothing but your W, and D2 other terminal is nothing but your X. Okay, we need to find this, and in between W and X, this is what your 1 kilo ohm. Can I say that in between W and X? Therefore, this is what is our 1 kilo ohm. Now, what about your D3? Your D3 is connected between W and Z. Let us say this is what is my Z. Between W and Z, therefore Z is having P side and W is having N side. Therefore, this is what we have. And what about X side? X, and this is what is your, therefore between X and Z you have, therefore Z is P side and X is N side. Therefore, this is what is your circuit, and this is nothing but your D3 and this is D4. Can I say this is what your circuit? Both are same. If you know voltage across this 1 kilo ohm, problem is over. Okay, now, and this is what your VYZ, which is a sine wave. This is nothing but your VYZ, which is a sine wave. What it may be, don't respond to actual input. You treat this, and VWX. If you know voltage at W, voltage at X, VW minus Vx is nothing but VWX. That is what we need to find. Okay, now tell me, we should know the status of diode. If you know the status of diode, problem is over. Therefore, tell me, when VYZ is positive, you open all the diodes. If you open all the diodes, I am not writing it, just visualize. Open this, open this, open, open, then there is no current which is flowing through it, then there is no drop, whatever voltage are applied, the same thing is coming here. If VYZ is positive, positive here, off, positive, off, all are off. Therefore, VYZ, if it is greater than 0, all diodes are off. Okay, when all diodes are off, right, this is open, this is also open, this is open, this is also open, and there is a resistor. I can say resistor is floating. What is the voltage? 0. Therefore, this is W, this is X. Okay, and this is what is your 1 kilo ohm, what it may be. Okay, then what is your VWX, P, and this is what is your Y and Z, V, Y, Z, which is negative, sorry, which is positive. For positive voltage, all are off. Therefore, what is VWX? VWX is 0 volt. Because everything is floating, there is no current flowing through resistor. If there is no current flowing through resistor, then I into R, I is 0, therefore voltage drop will be 0. Okay. Now case 2. Case 2. When VYZ is negative or less than 0 volt. Okay. Then if it is negative, negative means this is minus, this is plus. Then all will be on. Then all will be on. Therefore, because all are ideal, all diodes are on. All diodes are on. If you are able to visualize, fine. If you are not able to visualize, you have to take, first of all, open all the diodes and you will get it. Okay, then fine. Then what is the circuit when all diodes are on? Like this is on, this is on, this is also on, this is also on. Now you have a resistor in between. This is your Y and this is what is your Z and this is what is VYZ. Okay, and this is 1 kilo ohm, this is also 1 kilo ohm, and this is what is your W and this is what is your X. When all are on, then tell me what is VWX. Right, this is short circuit, right, and this is short circuit. Therefore, what is, can I say this is short in parallel to a resistor. Similarly, this is also short. short in parallel to a resistor. Therefore, what is voltage across a short circuit? This is nothing but a short circuit. Therefore, voltage across a short circuit is 0. In this case also, if all are on, your VWX is also 0 in this case. Here also means for any input, whatever may be the input, your output is always 0. Your output is always 0. Therefore, what is the answer? Your answer is 0 for all t. Therefore, answer is D. Answer is D. I hope everyone understood. Okay, it is just to confuse different terminals are there. But once you write in a way, and then if you know the status of diodes, and if you find WX, you'll get the answer. Okay, done. I hope everyone understood, because what is this? This is nothing but a short in parallel to 1K. Therefore, it is 0, 0. It is simply 1K is coming to V. Whatever voltage are applying, that will come to 1 kilo ohm resistor. That's it. Okay, take it. Means even though your input is a sine wave having, this is 100 volt, 1000 volt, and this is minus 1000 volt, but your output is 0. Your output is 0. For any input, for all time t, your output is 0. That's why answer is D. I think everybody understood the procedure, right? Fine. Then we will see Zener diode regulator. See, all clippers are something like this. We need to manipulate with the diode status and network analysis. We'll get the answer. Okay. But Zener diode is little different. Only when Zener diode is in breakdown, then only it will act as a battery, then only it will give you constant voltage. Okay. What is the breakdown voltage? That is what output voltage. That is what we will see. Then we will solve remaining classroom workbook problems. I'll explain what is Zener regulator and how it is regulating and why output voltage is almost constant. Then we will see problems. I'll give you 1.5 minute time. Try to solve it. Means try to note in your notebook. Okay. Now the typical circuit of Zener regulator is this is your Zener diode, and then people represent with Zener breakdown voltage, which is Vz, and this is what is your load, okay, RL, and this is what is our output voltage Vout, and this is what your source resistance Rs, and this is what is our input voltage, or people call it as source voltage Vs, or line voltage. This is also called as line voltage. Okay. Now here, what are the variations? Right. Now, even though your line voltage is varying, whether it is increasing or decreasing, we don't know. My output voltage to be constant. I am speaking about voltage regulator. Okay. I think we had seen already regulators in the case of op-amp, right? But those circuits are useful even for lower voltage regulation. If you want to get 1 volt regulator output, we can get, but here we cannot get 1 volt regulator output, because the regulator output voltage is nothing but your Zener breakdown voltage, because it is in parallel. I told you, right, if Zener diode is in breakdown, it is a battery. That battery voltage only you are going to get. For different Zener diodes with different breakdown voltages, you will get different regulated output voltages. That is what people used to use earlier. But now if you want to get 1 volt, 1.2 volt and all, that is very difficult to get Zener diode breakdown. Then we cannot use Zener regulators to get 1 volt, 1.2 volt and all. Okay. That is the limitation of Zener regulators. But earlier we deal with, like, if you take IC 741 op-amp, 1990, 2000, in that range, we used to use plus or minus 15 volt, plus or minus 10, plus or minus 5 volt, all those things. Then people used to use Zener regulator. Okay. Now, if you see, even though your line voltage is varying, but I am expecting my output voltage to be constant. Even though my load is changing, or load current is changing, I am expecting my output voltage to be constant. But how it is constant, I will explain. Remember, this is true only when Zener diode is in breakdown. If Zener diode is not in breakdown, it will not act as a battery. It will be like forward bias or reverse bias, normal PN junction diode. Okay, that is what I told, right? Only when the Zener diode is in breakdown, then only it is almost acting as a battery. This is what is your VZ, and the corresponding current. This is reverse saturation current, but the starting of breakdown, this is what people call it as high Z minimum. Maybe after some time, and then this is what is associated with IZ maximum. Okay, and then corresponding the change in the Zener voltage. Okay, almost zero. But if you take it within a small change in voltage above the breakdown voltage, it can support from minimum to maximum. This is what is practical scenario. But if I take ideal scenario, which is not there, but then for a small change, the small change is 0. For 0 means, 0 change means it is almost VZ only. For VZ, it can support current from minimum to maximum. Why it is defined with maximum? If you cross this current, your Zener diode will dissipate more and more power, then it may be burnt. Therefore, it is defined with power dissipation. The maximum current is defined with maximum power dissipation from your Zener diode. Now, having said that, now I explain how it is regulating it. For that, we need to have some KCL and then KVL. Remember, if Zener diode is in breakdown, when Zener diode is in breakdown, this is what? When Zener diode is in breakdown, then the Zener diode, when it is a reverse bias, only in reverse bias you are getting breakdown, right? Then this is what is going to act as a battery. When I say VZ is represented, the breakdown voltage just beside your Zener diode, which is another breakdown voltage, then it is nothing but your Zener diode. This is what is your ideal case, which I already told yesterday. Then if you take practical scenario where a small variation is VZ with respect to minimum to maximum current, then you will have a resistor and then battery. This is what is your Zener resistance, right? This is your VZ and this is your RZ. This is what your practical diode. Maybe for the time being, let me take ideal scenario. When Zener diode is in breakdown, this is nothing but a battery. Then if it is a battery, in parallel voltage is constant, your Vout will be equal to the Zener breakdown voltage. If you change a different Zener diode with a different breakdown voltage, your output voltage will be corresponding to that breakdown voltage. Okay, fine. Now let me explain how it is regulating your line voltage, how it is regulating your load. That's what it is called, line regulation and load regulation. Even the load is changing from minimum to maximum. But remember, for all values of load, your output voltage will be constant. No, only for some range of load change, then only your output voltage will be constant. Similarly, only for range of your input signal, your output voltage is constant. Going forward, when we solve the problems, for what input range, your output is constant. For what load change, your output is constant. These are all the problems which we need to solve. Okay, that's fine. For now, let me explain. we need to have some equations KCL. First of all, this is what is your source current IS, which you are getting from your line voltage. Then this current is equal to this current plus this current. This is nothing but your Zener current. Let me call this as IZ, and this is nothing but your load current IL. Okay. Therefore, now tell me what is your V out. We know that your V out is equal to what? IL into RL. Okay. Your V out is equal to IL into RL. Now we want to keep, I'm just explaining. Now I'm explaining first of all line regulation. Line regulation. When I explain line regulation, you have to keep load constant. You have to keep your load constant. Let us say RL is constant. Then I'll speak about load regulation. Okay. Then when I say line regulation, what does it mean? Let us say your Vs is increasing or decreasing. When Vs increases, right, then surely your Is will increase. When Is is increasing, we know that, therefore Is, what is Is? Is is nothing but KCL, Iz plus IL. Iz plus IL. This is what is very important KCL equation which we need to use later. Therefore now tell me your Is is increasing. When Is is increasing, you may say Iz will increase, IL also will increase. If source current is increasing, this current will increase, this current will increase. But remember, if IL is increasing and RL is constant, because I'm speaking about only line regulation, only line changes only, I'm trying to see what is your output voltage. Therefore, when RL is constant, this is constant. Only when IL is constant, then only your Vout is constant. And we know that Zener diode is nothing but a battery. In parallel, voltage is constant. To make Vout constant, whatever extra current you are getting from your source, that will be bypassed by your Zener diode. Means the Zener current only will increase, not IL. Therefore, only Zener current will increase and your IL will be constant. To keep it is constant, to keep Vout is equal to IL into RL constant. Therefore, what is your Vout? Your Vout is Vz, that is constant. That is constant by your Zener diode. Why? Whatever extra current you are getting from your source, that will be bypassed by your Zener diode. That will be bypassed by your Zener diode. It will not pump into load. If it is pumping into load means when you take RL constant, surely your Vf will be affected. But Zener diode is nothing but a battery, then it will not change the voltage. To do not see the change in the voltage, extra current will be bypassed by your Zener diode. Here the key note is, if I increase my line voltage further and further, your Is is increasing further and further, then your Iz will increase further and further. If that Iz is crossing your Iz maximum, remember your Zener diode will be burnt, then it will not act as a regulator. That's why your line voltage is also having some range. It should not cross some range. If it is crossing some range means your Zener diode also will be burnt. But anyway, from normal power supply, we know that the line fluctuation won't be that much. Therefore, it will withstand. Okay, that is worst case. Now let me speak load regulation. When I say load regulation, when I speak about load regulation, I need to keep line voltage constant, else it is difficult to understand. Therefore, your line voltage Vs constant. If Vs is constant, your Is is constant. If source voltage is constant means your Is is constant. Why? What is your Is? Your Is is nothing but, this is what your Vout, equation 1. Okay, that's fine. Therefore, your Is is constant. Therefore, now tell me, as your RL is increasing or decreasing, what it may be. As RL is increasing, then you know, as RL is increasing, then what about your Vout? Your Vout is equal to IL into RL. If RL is increasing, but to keep Vout constant using Zener diode, right? To keep Vout constant, when RL is increasing, right, whatever IL which is what is flowing through it, because when Is is constant, Iz is constant, IL is constant. If IL is constant but I am increasing my RL, If RL is increasing, then your Vout will be increasing if IL is constant. To keep Vout constant, your IL will decrease. IL decreases due to IZ increment. IZ increment. Your IZ will be increased automatically. Therefore, what is that? Your IL is equal to IS minus IZ. That is what your KCL, right? Your load current is equal to source current minus Zener current. You know, automatically your IZ will increase. Your IZ will increase automatically to keep Vout constant. Therefore, your IL will decrease. When IL is decreasing, then you know what will happen? Therefore, your Vout is constant, is equal to IL into RL. Even though RL is increasing, your IL will decrease. Therefore, this is constant. This is what is your water. Therefore, the Zener current is adjusted. Remember, the Zener current is adjusted in between, but it should be in between IZ minimum to IZ maximum to keep output voltage almost at Zener voltage or constant voltage. That is what your constant voltage. Therefore, because of current adjustment through Zener diode from minimum current to maximum current, it is giving output voltage almost constant, which is nothing but Zener voltage. I hope everybody understood. Okay, this is what is the theory. Therefore, we will see that. What I mean, now both are happening at the same time. Line voltage is changing, load is also changing. Ultimately, your IZ will be adjusted such that your Vout is equal to IL into RL. Even though both are changing, right? Ultimately, your Vout should be constant. That will be taken care by your Zener diode. Okay, fine. Now take it. Then after that, we'll solve other problems. But remember, this is true only when the Zener diode is in breakdown. If Zener diode is not in breakdown, let us say in what you call in reverse bias, Zener diode is nothing but open circuit. If it is open circuit, nothing, no regulation. Your Zener diode is not acting as a battery. This is true only when it is in breakdown. Okay, I'm stressing this point again and again. That is very important. Okay, take it. I will give you 2 minutes time, then we will solve problem number 6, classroom workbook problem number 6. For the Zener regulator circuit shown below, find V0. Okay, problem number 6. Option A 5 volt, option B 6 volt, option C 7 volt, option D 8 volt. And this is what your source resistance RS. Okay. Tell me, what is your output voltage? What is your output voltage? See, when Zener diode is in breakdown, right, then it is acting as a battery, which is nothing but 6 volt. The same 6 volt will be your output voltage. Okay. Therefore, what is the answer? 6 volts. Right? Answer is 6. Because whatever voltage you have across the Zener diode, right? If that is in breakdown, then the same 6 volt will come at the output. But remember, answer is not 6 volt. I was saying always, if Zener diode is in breakdown, then only 6 volt will come here. But I know that you will also say Zener diode is not in breakdown. Again, how do you know, or how can we find whether Zener diode is in breakdown or not? I told you the technique. If you want to find the status of diode, whether it is in reverse bias, forward bias, breakdown, the technique is open the diode. Open the diode to find its status, twin status, right? When you open the diode, what you get? When you open the diode, this is 100 ohm, this is 100 ohm, but now this is what is 10 volts. It is network analysis, right? And bring back your diode. When you bring back your diode, this is what it is. Okay? Now tell me, surely it is in reverse bias. I agree. But now find voltage across open terminals. 100, 100, both are same. Out of 10, 5 here, 5 here. Therefore, what is the voltage across this? That voltage across your Zener diode will be 5 volt. But what is the voltage required? What is the voltage required such that it will enter into breakdown? I don't want reverse bias. I don't want forward bias. I want Zener breakdown. It should be entering into Zener breakdown, right? Therefore, once it is entering into Zener breakdown, at least you need to apply more than or equal to 6 volts across the Zener diode. Then only it will act as a battery and then give you 6 volt. Now you know what happened. See, now the scenario is, this is what is your, let us say this is what is your VZ, that is what is 6 volt. Then it is supported by IZ minimum and supported by, let us say, IZ maximum. Therefore, now this is what is our breakdown case. But now where are we? According to this, now the Zener diode is having 5 volt. 5 volt is nothing but what? Here. Now we are here. Then what is the current? The current is almost 0. This is nothing but a reverse saturation current, which is almost 0. Therefore, this is nothing but your reverse bias. Zener diode is in reverse bias, and this is what is our Zener breakdown. Zener breakdown. Therefore, what is the status of diode? Your Zener diode is in reverse bias. Zener diode is in reverse bias. If it is in reverse bias, it is open circuit. When this is what is open circuit, then what is your output voltage? Therefore, it is off. Reverse bias means off. Off means open circuit. Then what is your circuit? Then your circuit is simply, that's it. This is what your VI, which is, then this is what your 100 ohm, and your load is also 100 ohm. Then tell me what is your Vout? Vout is nothing but your VI by 2. Therefore, when VI is 10 volts, your V0 is, when VI is 10 volts, your V0 is 5 volt. But it is unregulated. If VI changes, unregulated. Why unregulated? If VI changes, there is nothing, it is potential divider. Your V0 also changes. There is no Zener diode. Okay? It is unregulated output voltage 5 volt. Therefore, this is unregulated. It is not regulated. Because there is no circuit. It is simply potential divider network. Okay? Therefore, what is your output? Your output is 5 volt. Therefore, tell me, we are here. If you want to enter into breakdown, what to do? If you want to enter into breakdown, what to do? You need to apply the input voltage at least 12 volt. When you apply your VI at least 12 volt, then in open circuit case, you will see 6 volt, then it will enter into breakdown. If VI is greater than or equal to 12 volt, that is what is the observation if you want. Therefore, only if the VI is greater than or equal to 12 volt, then Zener diode will be in breakdown. Will be in breakdown. Then only regulation. Then only regulation. Therefore, what is VI minimum? The minimum voltage for which your Zener diode is doing regulation is nothing but 12 volt. This is what is our minimum voltage. Less than minimum, no regulation. Okay? Okay, take this is what your observation. This is what your input voltage minimum. Similarly, your maximum, the VI maximum is limited by maximum Zener current. When we solve the further problems, you will understand. Okay. But VI minimum is associated with keeping Zener diode in breakdown. If VI is less than 12 volt, it won't be in breakdown. There is no regulation. Simply voltage divider network. Your output will be tracking to your input. If VI changes, output also changes. If load changes, your output changes. There is no tracking. Okay. I think our session is almost done. We have 3 to 4 minutes. Then you try to note down. At least anyway, I need to give like 1 or 2 minutes. Then we have only 1 or 2 minutes left. We cannot solve next problem. Then we will continue in the next session. Okay. We will continue from problem number 7. Okay. Thank you.